Welcome to Conscious Frequency. I'm your guide on this journey into the profound and the beautiful. Settle in, breathe deep, and allow the gentle currents of wonder to carry you. Today, we embark on an exploration of time itself, not as a relentless march, but as a fluid, malleable force. We'll delve into the universe's grandest timescales, where stars are born, live, and die, stretching our perception of existence. We'll uncover how the very fabric of spacetime can bend and warp, influencing the rhythm of cosmic events, and how this relates to our own experience of time. Prepare to be mesmerized by the quiet, enduring secrets whispered by the cosmos. As we begin, I invite you to find a comfortable position, perhaps nestled amongst your pillows, or reclined in a favorite chair. Let your surroundings fade. I'd love to know where in the world you're joining us from today. Share your location in the comments below. It's always a joy to see our conscious frequency community spread across the globe, united by curiosity. If the whispers of the universe resonate with you, and you find solace and wonder in these explorations, consider subscribing to Conscious Frequency. Click the notification bell so you don't miss our future journeys into science, philosophy, and the art of conscious living. Your support helps us continue to create these peaceful, informative spaces. Over the next 2.5 hours, we will traverse vast cosmic landscapes, from the delicate dance of subatomic particles to the majestic life cycle of stars. We'll ponder the nature of time, the elegance of relativity, and the deep philosophical implications of our place in the universe. Let your thoughts gently unfurl. Allow yourself to sink deeper into this moment, letting go of any urgency. This is your time to simply be, and to learn. But here's where it gets interesting. Our everyday experience of time, linear and unwavering, is just one facet of a much grander, more intricate reality. We feel time, don't we? Like a river constantly flowing, carrying us from the quiet shores of the past, through the fleeting present towards the misty horizons of the future. It's as steady as a heartbeat, as predictable as the sunrise. But science, in its beautiful, persistent way, whispers a different story, a story where time isn't quite so universal. Think about it. When you're lost in a captivating conversation, or perhaps staring up at a sky dusted with a million diamonds, doesn't time seem to stretch, to become a gentle, unhurried embrace? And then, when you're rushing, late for something, the minutes can feel like tiny, frantic birds, flitting away before you can even grasp them. Our inner clock, our intuition tells us time is fluid, personal. And science, it turns out, is starting to agree. For centuries, we imagined time as this grand, cosmic clockwork, ticking away uniformly for everyone everywhere. But then came a mind like Einstein's, a mind that dared to look at the universe not as separate pieces, but as a single, woven tapestry. He showed us that space and time aren't distinct entities, but are, in fact, intertwined. He gifted us the concept of a spacetime, a four-dimensional continuum, a unified fabric that binds the 3 dimensions of space with the dimension of time. Imagine space and time as threads, spun together into a single shimmering cord. That's spacetime. And this spacetime, it's not just some passive stage upon which the cosmic drama unfolds. Oh no, it's a dynamic, living entity. It can be nudged, it can be bent, it can even be warped. What causes this warping? Mass and energy. The more massive an object, the more it presses down on this cosmic fabric, creating a dip, a curve. And this curvature, this subtle bending of spacetime, is what we experience as gravity. It's not a force pulling us, but rather the universe guiding us along the contours of this warped fabric. This leads to something truly mind-bending, the illusion of simultaneity. Because spacetime is so intimately connected to motion and gravity, what appears to happen at the same moment for you might not for someone else moving at a different speed or standing near a massive object. Imagine 2 perfectly synchronized clocks. If one of those clocks begins to travel at an incredibly high speed, or is placed very close to a black hole, its ticking will actually slow down relative to the stationary clock. So, the idea that we can all agree on what no is everywhere in the universe simultaneously, that's a beautiful simplification, a comforting illusion. Let's try to picture this. Imagine spacetime as a vast, invisible trampoline. Massive objects like stars are like heavy bowling balls placed on this trampoline, causing it to dip and curve. This curvature is what we perceive as gravity, and it also subtly affects the flow of time around these massive objects. The deeper the dip, the slower the time flows in that region. It's like walking on a gently sloping hill versus a steep incline. The effort, the experience, is different. So, if massive objects can warp spacetime, what does this mean for our understanding of time's flow, especially near the most massive and energetic objects in the universe, like stars on the brink of collapse, or the enigmatic black holes? It suggests that time itself can be a little flexible. And this brings us to you. Have you ever felt time slow down or speed up in your own life? Perhaps during moments of intense focus, or deep relaxation, or even during a sudden scare? Share your personal experiences in the comments below. We'd love to hear how you perceive the rhythm of time. Now, here's the beautiful part, the really soft revelation. This warping of space-time, this cosmic bending and stretching, isn't just some abstract idea confined to chalkboards and distant galaxies. Oh no. It has tangible, real-world effects on how we measure time itself. It's like discovering that the very fabric of existence plays favorites, subtly altering the rhythm of existence depending on where you are and how you're moving. This is where we meet the concept of time dilation. Imagine, if you will, that time isn't this perfectly uniform, unyielding tick-tock for everyone. Instead, it's more like a gentle, adaptable melody, played at slightly different tempos for different listeners. The core idea, a cornerstone of Einstein's beautiful theories, is that time passes slower for an observer who is moving relative to another observer. Think of it as a subtle cosmic courtesy, a way the universe acknowledges your journey. And it's not just about speed. Gravity, that invisible embrace that holds us to this spinning planet, also plays a role. The stronger the gravitational field you find yourself in, the slower time will gently nudge its way forward. It's as if gravity itself has a way of slowing down the clock, making each moment stretch a little longer, a little more deliberate. Let's try to picture this with something called the twin paradox. Now, don't let the paradox part scare you. It's more of a delightful thought experiment. Imagine two twins born at the exact same moment. One twin stays here on Earth, living a perfectly normal life, experiencing time as we usually do. The other twin, however, hops aboard a spaceship, a vessel capable of traveling at speeds incredibly close to the speed of light. They venture out into the cosmos, perhaps for what feels like a few years to them. When they finally return to Earth, they'll find something astonishing. Their Earth-bound twin will be significantly older. The twin who traveled at near light speed will have experienced less time. It's as if their personal clock, their internal rhythm, was set to a more leisurely pace because of their rapid journey. It's a profound illustration of how motion itself can stretch out time. Then there's the gravitational side of things, which is truly fascinating. Think of time like a river. In the calm, open waters of space, far from any massive objects, it flows smoothly, predictably, like a gentle current. But when you approach a deep, powerful whirlpool, that's your strong gravitational field, perhaps the crushing embrace of a black hole or a neutron star, the water's flow becomes sluggish, swirling, and much slower. And time, like the water, slows its pace in these intense gravitational currents. The closer you are to a massive object, the more time itself seems to linger, to take its sweet time. This isn't just a theoretical musing, it's a fundamental aspect of how the universe operates, a subtle but powerful force shaping the very flow of existence. And the really mind-bending part, we have experimental proof of this. It's not just science fiction. Back in the day, scientists performed an experiment called the Heffel-Keating experiment. They strapped incredibly precise atomic clocks onto airplanes and flew them around the world. When they compared these clocks to identical ones that stayed put on the ground, they found tiny, but measurable, differences. The clocks that had traveled, experiencing both speed and a slightly weaker gravitational pull at altitude, had ticked just a fraction of a second slower. It's like the universe was subtly whispering, see, time is relative. And in our everyday lives, we rely on this phenomenon constantly, even if we don't realize it. The GPS satellites that guide your car, that pinpoint your location with such uncanny accuracy, they're constantly moving at high speeds and are in a weaker gravitational field than we are on Earth's surface. If their internal clocks weren't meticulously adjusted to account for both special relativistic time dilation, due to their speed and general relativistic time dilation, due to gravity, your navigation system would quickly become wildly inaccurate. It's a constant silent correction, a testament to how these profound cosmic principles are woven into the very fabric of our modern world. So, with this understanding, this gentle realization that time itself can bend and sway, what happens when we apply these principles to the most extreme environments in the universe, like those surrounding colossal stars, or even the enigmatic mouths of black holes? What secrets might time itself hold in those places? To understand time's secret life in the cosmos, we must first look to the stars themselves, the ultimate laboratories of spacetime. Imagine, if you will, drifting through the deepest, most silent reaches of space. It's not entirely empty, though. Scattered across the vastness are these immense, ethereal clouds, vast molecular clouds. Really? They're like cosmic nurseries, whispered into existence by the gentle breath of creation. These clouds are made of the most fundamental ingredients: hydrogen, helium, and a scattering of heavier elements, all bound together by an invisible persistent force. And that force, my friends, is gravity. It's the universe's quiet conductor, orchestrating cosmic ballots on scales we can barely comprehend. Within these nebulae, these grand, swirling tapestries of gas and dust, gravity begins its slow, deliberate work. It's like a giant, ethereal cloud of cosmic dust and gas. Slowly, gently, gravity begins to gather these particles, like a soft hand cupping a handful of mist, drawing them closer and closer until a new, luminous heart begins to beat. As gravity pulls these particles inward, the cloud begins to condense. It spins, it flattens, and at its center, a dense knot of matter starts to form. This is the protostar phase. It's a star in its infancy, a celestial embryo. The core of this protostar is getting hotter, hotter and hotter, as more and more material is drawn in, like a cosmic snowball rolling downhill. But it's not quite a star yet. The pressure and temperature in its core haven't reached that critical point, that fiery threshold, where the true magic happens. Around this nascent star, the infalling gas and dust often forms a swirling, flattened disk, a cosmic pancake, if you like. This is the accretion disk. It's a feeding ground, constantly showering the protostar with more material, fueling its growth. You can almost feel the energy building, a silent hum of potential, a promise of light yet to be born. And then, the moment arrives. The core of the protostar becomes so incredibly hot and so incredibly dense that something extraordinary occurs. The atoms of hydrogen, the most abundant element in the universe, are squeezed so tightly together they begin to fuse. They merge, transforming into helium. This is nuclear fusion, the very engine of a star. It's like striking a match in the deepest dark, a sudden, brilliant illumination. This ignition, this glorious burst of energy, marks the birth of a main sequence star. It's the moment our protostar steps onto the cosmic stage, bathed in its own glorious light. It's a stable, burning entity, a beacon in the darkness, for millions, billions, even trillions of years. And it all comes back to gravity, doesn't it? Gravity is the architect, the relentless builder, pulling the stardust together. But it's also the ultimate arbiter of a star's destiny. It's the force that fuels the fusion, and it's the force that will, in time, determine how this star will eventually fade, or perhaps explode in a spectacular farewell. This same gravity, the silent sculptor of stars, also has a profound and subtle way of interacting with the very fabric of spacetime around it. Once a star ignites, how does its immense mass and energy begin to interact with the very fabric of spacetime? Take your time with this thought. For most of its existence, a star is in a state of delicate balance, and this balance subtly shapes the spacetime around it. It's a kind of cosmic equilibrium, a quiet hum that defines its prime. We call this the main sequence. Imagine a star at its heart, a furnace of unimaginable power. Inside this fiery core, atoms of hydrogen are being squeezed and fused together, transforming into helium. This process, this nuclear fusion, is like a constant, gentle explosion, radiating an immense outward pressure. Now, think about gravity. Gravity, that invisible hand, is always trying to pull everything inward, to collapse the star into a tiny, dense point. For billions of years, these two forces are locked in a profound dance. The outward push from fusion is perfectly matched by the inward tug of gravity. It's a cosmic tug of war, but instead of a winner, there's a beautiful, stable stasis. This is what defines a star on the main sequence, a state of hydrostatic equilibrium. Our very own sun, that benevolent beacon warming our planet, is right in the middle of its main sequence phase. It's been doing this for about 4.6 billion years, a steady, reliable glow, and it's expected to continue this for another 5 billion years or so. That might sound like an eternity to us, but in the grand cosmic scheme, it's just a chapter, a long luminous middle act. Now, here's where things get really interesting. The mass of a star is the ultimate arbiter of its life story, especially its time on the main sequence. Think of it like this: a bigger engine needs more fuel. More massive stars have a stronger gravitational pull, which means their cores are squeezed even tighter, leading to much faster and hotter fusion. They burn through their hydrogen fuel at an absolutely astonishing rate. These giants are incredibly bright, blazing with a fierce, blue-white light, but their lives are, in a cosmic sense, fleeting. They might only live for a few million years. On the other hand, smaller, less massive stars like red dwarfs are the slow burners. They fuse their hydrogen gently, and their lives can stretch for trillions of years. Our Sun, being a medium-sized star, sits comfortably in the middle with its billions-year lifespan, and this immense energy output, this relentless fusion, isn't just about light and heat. It's about shaping the very fabric of the universe around it. The sheer power radiating outwards from the core creates a gravitational potential well, a deep dimple in spacetime. It's like a perfectly inflated balloon, its surface stretched taut by the air within. The star's energy is that air, and the balloon's surface is spacetime itself. This outward flux of energy, born from the heart of fusion, is what helps maintain that characteristic warp, that gentle curvature of spacetime that we associate with gravity. You see, a main sequence star is like a perfectly balanced dancer, holding a pose with immense grace. The outward push of their energy, the fusion happening deep within, perfectly counters the inward pull of gravity, creating a stable, luminous presence in the cosmic ballet. It's a breathtaking display of balance, a steady heartbeat in the vastness. But what happens when this delicate balance is disrupted, and a star begins to age? What are the first whispers of change in that steady cosmic rhythm? If you could witness any stellar event, what would it be? Share your cosmic dream in the comments below. I'd love to hear what sparks your imagination. But here's where it gets interesting. Even stars, in their long lives, experience profound transformations that echo through the spacetime around them. Think of our Sun, or any star like it, as a magnificent, cosmic furnace, diligently burning its fuel. For billions of years, the primary ingredient, the very essence of its brilliant light, has been hydrogen. Deep within its core, under unimaginable pressure and heat, hydrogen atoms are being squeezed and fused together, creating helium and releasing an immense outpouring of energy. This is the engine that keeps a star alive, that bathes planets in warmth and light, that paints our sky with its presence. But even the most abundant fuel eventually dwindles. Imagine a hearth after eons of burning, slowly, supply, running out of its driest twigs. The vigorous, steady flame in the core begins to falter. The fusion, that relentless dance of atoms, starts to cease in the very center. It's not a sudden death, mind you, but a profound shift, a quietening of the primary engine. Now gravity, that ever-present force, doesn't just give up. It's always there, a constant, gentle, insistent tug, trying to pull the star back in on itself. With the outward push from fusion weakening in the core, gravity begins to win that subtle battle. The core, now mostly made of helium and no longer actively fusing, starts to contract. It squeezes itself tighter and tighter, like a fist clenching. And as it contracts, it gets hotter. Oh, so much hotter. This intense heat, generated by the contracting core, ignites the hydrogen that surrounds it. It's like finding a new kind of tinder, a layer of fuel just outside the now dormant central furnace. This hydrogen, in a shell around the inert helium core, begins to fuse with a renewed, and frankly quite spectacular, vigor. This shell burning is incredibly energetic. It's like a sudden surge of power, a more intense burst of creative energy, after a period of quiet contemplation. And what happens when this shell burning intensifies? Well, it generates more energy than the core fusion did. This surge of outward pressure, pushing against the star's outer layers, becomes overwhelming. The star's outer shell, the vast expanse of its atmosphere, begins to expand. It swells and swells and swells like a breath drawn in and held, then released with immense force. As these outer layers expand, they also cool. Imagine a hot ember being fanned, but then that fan is suddenly used to spread the embers over a much larger area. The individual points are still hot, but the overall glow becomes more diffuse, more spread out. This expansion causes the star to change color. The hotter, bluer light from its earlier, more compact phase gives way to a deeper, warmer hue. It turns reds. It becomes a red giant. It's a phase of immense, almost benevolent expansion. The star's surface might be cooler, its light a deeper, richer crimson, but its overall luminosity can actually increase because of its sheer size. It's like a tiny, intensely bright candle being replaced by a vast, glowing bonfire, its light reaching much further, even if the flame itself isn't as searingly hot. And this colossal expansion, this dramatic increase in size, doesn't go unnoticed by the fabric of reality itself. Spacetime, that invisible, elastic sheet upon which everything rests, is subtly but significantly affected. While the star's total mass might not have drastically changed at this point, its star's distribution has. It's like taking a heavy ball and spreading its weight out over a much larger surface. The indentation it makes on that elastic sheet becomes wider, shallower, but still undeniably present. The curvature of space-time around this burgeoning red giant is altered, its gravitational influence extending further, albeit in a less concentrated way. It's a gentle, widespread reshaping of the cosmic landscape. It's a bit like a fire that has burned all its immediate fuel. Instead of dying out, it suddenly flares up, consuming the surrounding wood, causing the whole structure to swell and glow with a deeper, more diffused light. The form has changed, the intensity has shifted, but the presence remains, perhaps even more profound in its gentle embrace. As stars continue to evolve, what happens when they start fusing heavier elements, and how does this further alter their relationship with space-time? Now, here's the beautiful part, isn't it? The internal alchemy of stars leads to even more dramatic changes, both for the star itself and for the very fabric of space-time it inhabits. It's like a grand cosmic dance, a slow unfolding of potential. For stars like our own sun, the journey through helium fusion is a bit like a hesitant, yet powerful awakening. As the hydrogen in the core runs low, the core begins to contract, heating up even more. And then, something truly remarkable happens. The helium, which has been patiently waiting, begins to ignite. For these lower mass stars, this ignition isn't always a gentle simmer. It can be quite a sudden, explosive event of helium flash. Imagine a quiet room suddenly filled with a warm, bright light. That's the essence of it. This flash is the moment helium nuclei, those two protons and two neutrons, start to fuse together, transforming into something new, carbon and oxygen. It's a profound shift, a fundamental change in the star's very being. The precise way this happens is through a beautiful dance of particles called the triple alpha process. Think of it like this: two helium nuclei, which we call alpha particles, can briefly stick together, forming an unstable beryllium nucleus. But this beryllium is fleeting, like a whisper in the cosmic wind. It needs to quickly capture a third helium nucleus before it falls apart. When it does, poof, you get a stable carbon nucleus. And this carbon can then capture another helium nucleus to become oxygen. It's a cascade, a series of cosmic handshakes that build heavier elements from lighter ones. It's the universe's way of saying, let's make something more interesting. Now, for the truly massive stars, the giants of the cosmos, this process is far more intense and layered. They don't just stop at helium. Their cores are so immense, so incredibly hot and dense, that they can continue this fusion process, creating heavier and heavier elements in a series of concentric shells. After helium fuses into carbon and oxygen, the core might contract again, heating up enough to fuse that carbon into neon, then oxygen, then silicon. It's like a celestial onion, with each layer cooking at a different temperature, fueled by the previous layer's success. Each stage requires more extreme conditions, hotter temperatures, and greater pressures. It's a relentless pursuit of complexity, a testament to the star's immense power. With each new element forged, the star's internal structure becomes more intricate, and so too does its gravitational influence. Think of the star's core as a series of nested ovens, each hotter than the last. Once one fuel burns out, the next oven ignites, cooking the next element in line, a process that steadily builds complexity and energy. This increasing complexity, this layering of different elements, creates a more intricate gravitational potential. It's like adding more and more intricate carvings to a sculpture. The contours become deeper, the shadows more pronounced. And as gravity's grip on these increasingly dense and complex layers intensifies, it can subtly, or perhaps not so subtly, begin to warp the very fabric of spacetime around it. Imagine a heavy ball placed on a stretched rubber sheet. The more massive and concentrated the ball, the deeper the dip it creates. And with these heavier elements, the star becomes a more potent sculptor of the spacetime canvas. This leads us to a profound question, doesn't it? What happens when the star can no longer fuse elements, and its internal structure, built through such a magnificent series of transformations, becomes unstable? What happens when the cosmic ovens finally run out of fuel? But here's where it gets interesting. The end of a star's fusion cycle is not a gentle fading, but often a cataclysmic event that violently reshapes spacetime. Imagine for a moment the very heart of a star, a furnace burning for billions of years. It's been diligently, tirelessly, forging lighter elements into heavier ones. Hydrogen into helium, helium into carbon, and so on, a cosmic alchemy powered by unimaginable pressure and heat. It's like a grand, celestial chef, constantly adding to its recipe, each new ingredient a step up the periodic table, a little more complex, a little more energetic. But then, the star reaches iron. And here, my friends, is where the cosmic kitchen closes. Fusing iron isn't like baking a cake, it's more like trying to unbake it. Instead of releasing a burst of energy, to fuse iron atoms together, you actually have to put energy in. It's a cosmic dead end, a fundamental law of physics that says, this far, and no further. The star, which has been a shining beacon of creation, suddenly finds itself in a desperate struggle. The outward pressure from fusion, the very force that has kept it puffed up and glorious against the relentless pull of its own gravity, begins to wane. And when that outward push, that stellar breath, finally falters, what happens next is profound. The iron core, no longer supported by the furious dance of fusion, begins to collapse. It's not a slow, graceful descent, it's a catastrophic implosion. Think of it like a towering skyscraper suddenly losing its central support beam. The entire structure, all those layers of star stuff, doesn't just fall, it implodes in an instant, inward, faster than you can even imagine, crushing itself under its own immense weight. Billions of years of stellar life, all that accumulated mass, all that gravity, now focused on a single, terrifying point. This inward rush of matter is so intense, so violent, that it creates an unimaginable density. The core compresses, electrons are forced into protons, creating neutrons in a process called electron capture. And then, something truly spectacular happens. The core becomes so incredibly dense, so rigid that it rebounds. It's like that skyscraper after imploding, suddenly springing back outward with an explosive force. This rebound creates a shock wave, a titanic wave of energy that blasts outwards, ripping through the star's outer layers. And that, my dear listeners, is a supernova. It's the ultimate celestial fireworks display, a moment of such extreme energy release that it briefly outshines entire galaxies. The star's outer layers are flung into the cosmos at incredible speeds, scattering newly forged elements like gold and silver, the very building blocks of our own existence, across the vastness of space. It's a violent rebirth, a cosmic scattering of stardust. But this isn't just a spectacular light show. This kind of immense, sudden violence, this catastrophic implosion and explosion, doesn't just affect the matter of the star. It affects the very fabric of reality itself. Einstein's beautiful theory of relativity tells us that massive objects warp spacetime, like a heavy ball placed on a stretched rubber sheet. A supernova, being an event of such extreme and rapid mass redistribution, creates ripples in this fabric. These are gravitational waves, invisible messengers that travel at the speed of light, carrying the echoes of that stellar death through across the universe. It's like dropping a pebble into a perfectly still pond, but instead of water ripples you have spacetime itself, rippling and vibrating from the star's final, furious breath. So, what remnants are left behind after a supernova, and how do these extreme objects further warp the fabric of spacetime? What curious cosmic leftovers does this stellar explosion leave in its wake? What does the idea of a supernova evoke in you? Share your thoughts and feelings. Take your time with this thought: the aftermath of a supernova, that spectacular fiery exhalation of a dying star, can leave behind objects so incredibly dense, they push the very boundaries of our understanding of matter and spacetime. It's a cosmic alchemy, a transmutation of the familiar into the utterly alien. Imagine, if you will, the heart of a massive star. After it has exhausted its nuclear fuel, it can no longer resist the relentless inward pull of its own gravity. This isn't a gentle yielding, it's a catastrophic implosion. The outer layers are flung outwards in that brilliant supernova display, but the core, it collapses with an unimaginable ferocity. The pressure becomes so immense, so utterly overwhelming, that it forces the very building blocks of matter to behave in ways we can barely conceive. Protons and electrons, those tiny, fundamental particles, are squeezed together with such violence that they merge, combining into neutrons. It's as if the universe is saying, you know what, let's just simplify. And in that moment of extreme compression, a neutron star is born. And the density, it's a concept that truly stretches the imagination. Think about it this way: if you could somehow scoop up just a single teaspoon of material from a neutron star, that tiny, almost insignificant amount would weigh billions of tons. Billions. That's heavier than all the cars on Earth, all the buildings, all the mountains, all compressed into something you could hold in the palm of your hand. It's like the universe took all the substance, all the stuff, and decided to pack it into the smallest possible container. This extreme density, this incredible concentration of mass, creates something truly awe-inspiring: an unbelievably strong gravitational field. At the surface of a neutron star, gravity is so powerful, so utterly dominant, that it's billions of times stronger than what we experience here on Earth. It's a gravitational embrace so tight, it warps the very fabric of reality around it. Picture squeezing the entire mass of a mountain, all its rock and earth and ancient trees, down into the size of a single sugar cube. That's the kind of extreme density we're talking about with a neutron star. And this incredible density, this compact power, creates a gravitational pull that profoundly bends the space-time around it. It's like dropping a heavy bowling ball onto a stretched rubber sheet. The sheet dips and warps, and anything that rolls near it will be pulled into its curve. And this intense gravitational field has a fascinating consequence, a subtle yet profound effect on time itself. It's called digravitational time dilation. For an observer standing on the surface of a neutron star, time would pass significantly slower than it would for someone observing from a safe distance, perhaps here on Earth. Imagine time itself becoming sluggish, heavy, like honey flowing in slow motion, simply because of the sheer weight of gravity. It's a testament to how deeply intertwined gravity and time truly are, two sides of the same cosmic coin. So, we've seen how even the remnants of stars can become these dense, exotic objects. But what happens when stellar remnants are even more massive, when the initial star was truly a giant? What happens when the collapse is so extreme, gravity becomes so overwhelmingly strong, that not even light, the fastest thing in the universe, can escape its grasp? That's a journey into a realm where the very laws of physics, as we know them, begin to fray at the edges, leading us to the ultimate cosmic mystery. But here's where it gets truly, wonderfully, terrifyingly interesting, doesn't it? The ultimate consequence of a massive star's death, a stellar titan that has burned brightly for eons, is an object so extreme, so utterly profound, that it warps the very fabric of spacetime into something we call as singularity. You see, when a star, one that's significantly heftier than our own sun, think more than 20 or 30 times its mass, exhausts its nuclear fuel, it can't quite support itself against the relentless inward pull of its own gravity. We've talked about white dwarfs and neutron stars, these incredible remnants. But for the truly colossal stars, the collapse doesn't stop there. It continues, compressing all that mass, all that stellar essence, into an infinitesimally small point. It's like taking a mountain range and squeezing it down until it's smaller than a grain of sand, but with all that mountain's weight still packed inside. And this is where we meet this event horizon. Imagine it not as a solid wall, but as a cosmic threshold, a one-way door. It's the boundary around this collapsed core where gravity becomes so overwhelmingly powerful that nothing, Absolutely nothing can escape its grip. Not a whisper, not a stray thought, and most importantly, not even light itself. Light, the fastest thing in the universe, the very messenger of the cosmos, gets trapped. It's the ultimate cosmic trapdoor, and once you cross that invisible line, there's no turning back. You're forever a captive of the black hole. At the very heart of this gravitational abyss, at the point where all that mass has been compressed, lies the singularity. This is where our current understanding of physics begins to, well, it begins to stutter, to falter, to frankly admit it doesn't have a clue. It's theorized to be a point of infinite density and zero volume. Imagine trying to divide by zero, but in a physical, tangible way. It's a concept so mind-bending, it feels like a riddle whispered by the universe itself. Our familiar laws, the ones that govern everything we see and experience, simply break down here. And the warping of spacetime, it's not just a gentle curve like placing a marble on a trampoline. Around a black hole, it's an infinitely deep well. Spacetime itself is so intensely distorted, so dramatically contorted that near the event horizon, space and time effectively swap roles. Imagine you're falling towards a black hole. As you get closer and closer to that event horizon, time for you would seem to slow down relative to someone far away. But for that distant observer, watching you approach, your time would appear to slow to an absolute crawl. At the event horizon itself, time dilation becomes infinite. It's like time itself is holding its breath, frozen in that moment of no return. Think of spacetime as a vast cosmic tapestry, woven with threads of space and time. A black hole isn't just a tear in that fabric, it's like punching an infinitely deep, perfectly circular hole right through it. All the threads, all the path, are drawn inwards, converging on that single, mysterious point. It creates a place where all directions lead only to the center, and the very concept of out simply ceases to exist. It's a place where the universe's most fundamental rules are rewritten, or perhaps, simply abandoned. So, if time itself gets so incredibly warped and distorted around these cosmic giants, how does that affect our perception of events happening near them? What would we see, or rather, not see, if we were to witness something falling into a black hole? It's a question that tickles the edges of our imagination, isn't it? Now, here's the beautiful part, isn't it? Observing events near a black hole's event horizon reveals the most dramatic examples of time dilation we can conceive. It's like looking at the universe's most extreme slow motion replay. Imagine, if you will, an astronaut, let's call her Alara, bravely venturing towards the inky embrace of a black hole. As she gets closer and closer to that invisible boundary, that point of no return, something truly profound happens to her experience of time. For Alara, time would feel, well, normal. Her heart would beat at its usual rhythm. Her thoughts would flow at their familiar pace. But for us, watching from a safe distance, bathed in the gentle light of distant stars, her clock would begin to drag. Each tick would stretch, becoming longer and longer, like molasses in winter. Her movements would appear to slow, her voice would deepen and stretch out, her very existence would seem to be caught in an increasingly viscous temporal current. This is gravitational time dilation, a direct consequence of Einstein's beautiful dance of gravity and spacetime. Massive objects like these cosmic behemoths warp the very fabric of reality around them, and where spacetime is warped, time itself bends and stretches. The closer you get to the source of that warp, the more pronounced the effect. Near a black hole, this effect becomes astonishingly dramatic. Now, as Alara continues her descent, she'd encounter something else, something rather unsettling. The tidal forces. Think of it like this: if you were to stretch a piece of taffy, you'd pull from both ends, and the middle would get thinner. That's essentially what happens to Alara. The gravitational pull on her feet, closer to the black hole, would be immensely stronger than the pull on her head. This difference in pull would stretch her, elongating her body, like a cosmic piece of spaghetti. It's a rather dramatic, if slightly morbid, visualization of gravity's relentless power. But let's return to our two perspectives, Alara's and ours, the distant observers. For Alara, she would cross the event horizon. It's a moment of passage, perhaps a fleeting sense of transition, but for her, time would continue. She would plunge into the unknown. For us, however, Alara would appear to slow down infinitely as she approached the horizon. Her image would become dimmer, redder, and seemingly frozen in time, forever hovering at the edge, a spectral silhouette against the cosmic backdrop. We would never actually see her cross. It's a profound cosmic irony, isn't it? She experiences the crossing, while we only witness the eternal approach. And what about what lies beyond the event horizon? At the very heart of the black hole, the singularity. This is where our understanding of time, and indeed reality, begins to fray at the edges. At the singularity, all the mass of the black hole is thought to be concentrated into an infinitely dense point. Here, our familiar laws of physics, the very rules that govern our universe, break down. Time, as we understand it, a linear progression from past to future, might simply cease to have meaning. It could become something else entirely, or perhaps nothing at all. It's a realm of pure speculation, a cosmic question mark, where the very concept of when might dissolve into a timeless void. It's a bit like watching a clock tick slower and slower as it approaches a waterfall's edge. From your perspective, standing safely on the bank, it seems to freeze, a silent sentinel just before it's consumed by the churning water. But for the clock itself, time continues its relentless march until it plunges into the abyss, its journey abruptly ended. How do these cosmic phenomena, which seem so alien and so impossibly distant, connect to our everyday experience of time? It's a thought that lingers, isn't it? What does the concept of time dilation near black holes make you wonder about the nature of reality? Perhaps it whispers to us that time isn't quite as fixed and steady as we often perceive it to be. But here's where it gets interesting, doesn't it? Even across the vastness of space, where gravitational influences can be so wildly different, the universe has its own subtle, almost whispered ways of keeping time. It's like imagine the universe as this colossal, ancient clockwork. Not a ticking, whirring thing you'd find on a mantelpiece, oh no. This is a clockwork of unimaginable scale, where the gears are galaxies slowly, majestically orbiting, and the hands are the cycles of stars, born in fiery nebulae, burning bright for eons, and eventually, gracefully fading. The grand waltz of stellar evolution, the stately procession of galaxies through the cosmic dark. These are the ticks and tocks of a clock so immense, we can barely begin to grasp its rhythm. Now, synchronizing such a clockwork, that's where things get wonderfully complicated. Think about trying to get two people across the globe to tap their feet at exactly the same moment. Even with our modern technology, there are tiny delays, aren't there? The speed of light, this ultimate cosmic speed limit, means that signals, information, even just the does light from a distant star, takes time to reach us. So, if you were trying to set your cosmic clocks, you'd have to account for the journey of that light. And then there's gravity. Oh, gravity. It's this invisible sculptor of reality, isn't it? It bends space, it warps time. So, a clock ticking near a massive star, or deep within the gravitational well of a galaxy, will tick just a little bit slower than a clock out in the quiet, emptier void. This isn't just theoretical, we see it. And that brings us to these remarkable cosmic timekeepers, pulsars. Imagine a neutron star, the collapsed heart of a star that once burned even brighter than our sun. These are incredibly dense, spinning at mind-boggling speeds, faster than a blender on high, some of them hundreds of times a second. And as they spin, they emit beams of radio waves, like cosmic lighthouse beams sweeping across the universe. When one of these beams happens to sweep across Earth, we detect a pulse. And these pulses are unbelievably regular, like the most precise metronome you could ever imagine. They're a natural, cosmic clock. But here's the truly fascinating part. Because gravity affects time, these incredibly precise pulsar signals, as they travel through the universe, can be subtly nudged by the gravitational fields of other celestial bodies. If a pulsar signal passes close to a massive planet, or even a faint cloud of gas, the extra gravitational pull can cause the signal to arrive at Earth a tiny fraction of a second later than it otherwise would. It's like the pulsar's heartbeat is momentarily slowed by the presence of something else in its path. And by measuring these minuscule shifts in arrival times, we get direct evidence, a whisper from the cosmos, about how gravity itself can stretch and warp the fabric of time. It's like, think of the universe as a grand orchestra. Each star, each galaxy, plays its part, contributing to this immense, unfolding symphony of existence. But the symphony is so vast, and the musicians are so incredibly far apart that coordinating their precise timing, ensuring they all play in perfect harmony, is a monumental task. And the very space between them, the invisible currents of gravity, can subtly influence when each note is played, when each beat is struck. It's a beautiful, intricate dance of time and space. If time is so relative, so malleable, so influenced by these cosmic forces, how does that change our understanding of causality? How does it affect the sequence of events, the very notion of what happens before, and what happens as after? It's a question that makes your mind wander, isn't it? A question that invites us to look a little deeper into the heart of reality. Take your time with this thought. The way time flows, and the way events unfold in sequence, is deeply tied to the fundamental laws governing the universe. It's like a cosmic dance, really, a choreography so intricate, so profound that it shapes everything we experience. Let's start with something we all intuitively grasp: causality. It's the simple, elegant principle that for every effect, there must be a cause, and that cause must come first. Think of it as the universe whispering, first this, then that. You drop a pebble into a still pond, and the ripples, the S-effect, spread outwards. The pebble hitting the water, the cause, happened before the ripples even began their graceful journey. This chain of cause and effect, this unbroken lineage, is the very backbone of how we understand reality. It's the reason we can make sense of the world, the reason we can predict, to some extent, what might happen next. Now, even when we venture into the mind-bending realms of Einstein's relativity, this fundamental principle of causality holds firm. His theories, while warping space and time in ways that can feel like magic, are actually designed to preserve causality. No matter how fast you're moving, no matter how strong the gravitational pull, an effect can never, ever outrun its cause. Imagine trying to send a message back in time to warn yourself about a spilled cup of coffee. Relativity, in its wisdom, says, nope, not happening. The universe, it seems, is rather insistent on keeping its appointments in the right order. But then, there's another player in this grand cosmic play, a concept that gives time its undeniable direction. It's called the second law of thermodynamics, and it introduces us to the idea of entropy. Entropy, in its simplest form, is a measure of disorder or randomness in a system. And the second law tells us that in any closed system, entropy always tends to increase. Think of your bedroom. If you don't actively tidy it, it doesn't spontaneously become neater, does it? It tends to drift towards a state of delightful, perhaps even creative chaos. This tendency towards disorder is what gives us the arrow of time. It's why we remember the past but not the future. Why we can unscramble an egg but we can't unscramble the universe. The universe as a whole is like one giant, incredibly complex system, and it's been on a journey from a state of incredible order, the Big Bang, towards a state of ever-increasing disorder. From the fiery birth of stars to the slow decay of galaxies, entropy is always nudging things along, pushing them towards a more diffused, less organized state. It's like building a magnificent sandcastle on a warm, sunny beach. The careful placement of each grain of sand, the sculpting of towers and moats, that's the cause and effect, creating order, a beautiful, temporary structure. But then, the wind begins to blow, the tide creeps in, and the relentless march of entropy takes over. The castle erodes, the sand grains scatter, and it gradually returns to the formless state of the beach. That erosion, that inevitable dispersal, that's the arrow of time made visible, the universe's gentle, persistent nudge towards greater disorder. And if the universe is indeed evolving towards greater disorder, towards a state of ultimate diffusion, what does this imply for the ultimate fate of those brilliant, burning stars we've been talking about? What does it mean for the cosmos itself? It's a question that hums with a quiet, profound significance, a whisper of what might lie at the end of this grand, entropic journey. Does the idea of entropy, this cosmic tendency towards disorder, change your perspective on time at all? Does it make you see the present moment, the order we experience, in a new light? I'd love for you to share your reflections on this. But here's where it gets interesting, doesn't it? The end of one star's life is intimately connected to the beginning of new cosmic chapters. It's a beautiful, almost poetic, dance of existence. When a massive star finally exhales its last breath, it doesn't just vanish. Oh no, It explodes in a spectacular, dazzling display called a supernova. Imagine the most brilliant fireworks you've ever seen, amplified a million times, painting the black canvas of space with unimaginable light and energy. What's left behind isn't emptiness, but rather these magnificent, expanding clouds of gas and dust. We call them supernova remnants. They're like the ghost of a star, still lingering, still shimmering with the echoes of its fiery past. And these remnants are extraordinary. They're not just pretty nebulae, though they certainly are that. They are cosmic treasure chests, brimming with elements forged in the star's core during its lifetime, and even more so during that final explosive act. Think about it: the very carbon that makes up your body, the oxygen you breathe, the iron in your blood, the gold in a treasured locket, all of it, or at least the atoms that eventually became those things, were once cooked up inside stars. And when those stars die, they scatter these precious elements far and wide. This is how the interstellar medium, that vast, mostly empty space between the stars, gets enriched. It's like a cosmic fertilizer. The debris from these supernovae, these clouds of gas and dust, are infused with all sorts of heavier elements, the very building blocks for future generations of stars and, crucially, for planets. So, that delicate nebula you might see in a photograph, that wispy and ethereal cloud, it's not just stardust in the poetic sense, it's literal stardust, carrying the ingredients for entirely new worlds, new solar systems, perhaps even new life. We're witnessing a grand, cosmic recycling program in action. Stars are born from these vast clouds of gas and dust. They live their lives, fusing elements in their cores, and then, when they reach their end, they become the very material that seeds the next generation. It's a continuous cycle of birth, life, death, and rebirth, all driven by the fundamental forces of gravity and the intricate dance of nuclear processes. It's a perpetual motion machine, powered by the universe itself, and the timescales involved are just mind-boggling. A star might form, live for billions of years, and then explode. But those remnants, those beautiful clouds, they don't just dissipate instantly. They can drift and expand for millions of years, slowly mixing with the existing interstellar gas. It takes an immense amount of time for these enriched materials to coalesce again, pulled together by gravity to form a new star. So, the journey from a star's death to the birth of a new one, and the materials that will eventually form planets around it, is a process that spans eons. It's a testament to the universe's patience and its incredible capacity for renewal. Think of it like a grand, ancient forest. Old trees, weathered by time and storms, eventually fall. They don't just disappear, they decompose, their matter returning to the earth, enriching the soil with nutrients. And from that enriched soil, new saplings sprout and grow, stretching towards the sunlight, continuing the forest's life. The fallen giants become the foundation for the new generation. Our universe, in a way, is a cosmic forest with stars as its trees and supernovae as the grand life-giving decay. So, as we gaze out at the night sky, at the distant gleam of stars, and the faint whispers of nebulae, it's worth remembering this incredible cycle. How does this ongoing process of stellar creation and destruction, subtly influenced by the very fabric of spacetime, shape the intricate and beautiful universe we observe today? It's a question that whispers through the cosmos, inviting us to ponder our own place within this grand, unfolding story. Now here's the truly beautiful, almost poetic part of our cosmic journey. When we lift our gaze to the night sky, to those distant, twinkling diamonds scattered across the velvet expanse, we're not just seeing them as they are right now. We are, in a very real sense, looking us back in time. It's all thanks to this fundamental, unyielding truth: light, as wondrous as it is, doesn't travel instantaneously. It has a speed, a finite, elegant pace. Think of it like this. The light that spills from a star, that ancient golden glow, has been on a journey that began years, decades, perhaps even billions of years ago. It's been traveling through the silent, vast ocean of space, a tireless messenger carrying its story. So, when that light finally reaches your eyes, here on this tiny blue marble, it's a message from the past. It's a glimpse of what that star was, not what it is in this very instant. It's like holding a letter in your hands. Imagine receiving a letter from a dear friend who lives on the other side of the world, a friend you haven't seen in years. That letter tells you about their life, their thoughts, their experiences, at the time they wrote it. Reading it sequentially, one page after another, gives you a sense of their past journey, their evolution. The universe in this analogy is like a colossal, infinitely unfolding collection of these letters, each one a testament to a moment long gone. This is how we understand the as observable universe. It's not just about how far we can see, but how far back in time we can perceive. The boundary of our observable universe is defined by the age of the universe itself and the speed of light. Light from the very edge of what we can see has been traveling since the universe was very, very young, carrying with it the echoes of the Big Bang. We're essentially looking at the cosmic infancy, the baby pictures of the universe, all thanks to this light, speed time machine. And it gets even more fascinating. The fabric of reality, this thing we call space-time, isn't always a smooth, flat sheet. It can be warped, curved, like a gentle ripple on a pond, especially around massive objects. Think of entire galaxies, or colossal clusters of galaxies. This extreme curvature can actually bend the path of light. It can act like a cosmic lens, distorting our view, making distances seem different, and sometimes, even hiding things from our direct line of sight. It means our perception of what's out there is also influenced by the very structure of the universe itself. So, if time is this fluid, relative thing, and our view of the universe is always a snapshot of its past, what does this really imply about our place in the grand, unfolding cosmic timeline? Are we simply observers of ancient history, or is there a deeper connection, a resonance, between our present moment and these distant, time-worn echoes? It's a question that humbles and expands the mind, isn't it? Thinking about all this starlight, all these ancient journeys, can be quite profound. So, let me ask you, what is one celestial object you often find yourself gazing at, perhaps on a clear night? And what does thinking about its light travel time, its own unique journey to reach you, evoke in you? Share your thoughts, your feelings, your cosmic reflections with us in the comments below. It's in these shared whispers of wonder that our collective understanding truly begins to shine. But here's where it gets interesting, doesn't it? The way we perceive time, this invisible river we're all floating down, it's not just governed by the grand, cosmic clockwork of physics. Oh no. It's also deeply, intimately tied to the very nature of our own consciousness. Think about it. Have you ever had a day where time just seemed to melt away? Perhaps you were lost in a passionate conversation, or deeply engrossed in a creative project. Suddenly, the sun has dipped below the horizon, and you wonder where the hours went. That's subjective time, our inner clock. It can feel like a lazy, meandering stream, or a frantic, rushing torrent, all depending on the landscape of our emotions, the focus of our attention, and the very activities that fill our moments. When we're bored, time can stretch out like a vast, empty desert, each second an eternity. But when we're engaged, truly present, time can become a swift, exhilarating ride, a blur of experience. And then there's the role of memory. Our memories are like the anchor points of our journey through time. They're the pebbles we collect along the riverbank, each one a distinct moment, a feeling, a scent. When we recall a vivid memory, we're not just remembering an event, we're re-experiencing a sliver of time. Our consciousness stitches these memories together, creating a narrative, a sense of continuity. Without memory, would time even have a meaning? It's the echoes of the past that give shape to the present, allowing us to feel the passage of years, the turning of seasons. It's how we know we've moved from that sun-drenched afternoon to this quiet evening. Philosophically, many have pondered whether consciousness itself is fundamentally anchored in the present moment. Perhaps our minds are like skilled weavers, constantly taking threads of sensory input from the immediate now and weaving them into a tapestry that includes the past and anticipates the future. We construct this narrative of time, this flow from the raw data of our experience. It's a beautiful illusion, perhaps this linear progression, but it's the one that allows us to navigate our lives, to learn, to grow, to love. It's the story we tell ourselves about where we've been and where we're going. And this is where things get truly mind-bending, isn't it? How does this internal, subjective experience of time, this feeling, this perception relate to the external, physical reality of space-time? Are they two sides of the same coin? Does our consciousness somehow shape or interact with the very fabric of time? It's a question that whispers at the edges of our understanding, a gentle invitation to explore the profound interconnectedness of everything. Our consciousness, in a way, is like a camera lens. Sometimes it's wide open, taking in everything, the soft light, the subtle textures, the distant hum of the universe. In these moments, time feels slow and rich, like a deep, resonant chord. Other times, it's zoomed in, focused intensely on a single point, a specific task, a burning question, and then time seems to rush by in a blur, a rapid succession of snapshots. The lens of our awareness, shifting and adjusting, influencing how we experience the grand, unfolding spectacle of existence. As we approach the end of our journey today, what overarching thoughts emerge about the profound interconnectedness of time, stars, and our own awareness? It's a question that lingers, a gentle hum beneath the surface of our waking thoughts, inviting us to consider the vast, mysterious dance between the universe and the witness within. Take your time with this thought. The universe doesn't just warp space-time, it can also send ripples through it, carrying profound messages. It's a bit like the universe has a voice, and sometimes it sings. So, what exactly are these cosmic whispers, these gravitational waves? Imagine space-time, that invisible four-dimensional fabric that holds everything together, like a vast, cosmic trampoline. Now, when something incredibly massive and energetic moves violently within this fabric, it doesn't just create a dimple, it sends out waves, disturbances in the very curvature of space-time itself. These are gravitational waves, predicted by the brilliant mind of Einstein, a direct consequence of his theory of general relativity. They're not like sound waves traveling through air, or light waves traveling through the vacuum, but rather, they are the vacuum itself, rippling. And what kind of cosmic events are powerful enough to strum this cosmic trampoline with such force? Think of the most dramatic spectacles the universe can offer. We're talking about the cataclysmic mergers of black holes, two of these infinitely dense points in space, spiraling towards each other, their gravitational pulls so immense they bend light itself, and then, with a final unimaginable embrace, they combine, sending out a powerful burst of these spacetime ripples. Or consider the explosive death of a massive star, a supernova, where the star collapses in on itself, then violently erupts outwards, a celestial fireworks display that can also shake the very foundations of spacetime. And then there are neutron stars, the incredibly dense remnants of these stellar explosions, colliding with each other in a cosmic ballad of immense gravitational force. These are the universe's most profound earthquakes, its most spectacular collisions, and they leave an indelible imprint on the fabric of reality. Now, detecting these waves is like trying to hear a whisper in a hurricane. They are incredibly, astronomically faint by the time they reach us here on Earth. Our observatories, like the incredibly sensitive LIGO and Virgo detectors, are marvels of engineering. They use lasers, split into two beams and bounced back and forth along incredibly long, evacuated tunnels. When a gravitational wave passes through, it imminently stretches and squeezes space-time, changing the distance the laser beams travel by an infinitesimal amount, a distance far smaller than the width of an atom. It's like trying to measure the ripple from a single raindrop on the surface of an entire ocean, but with astonishing precision. And what do these faint echoes tell us? They carry information that we simply can't get from light alone. Light can be absorbed, scattered, or blocked. But gravitational waves travel unimpeded, carrying the raw, unadulterated story of the most violent events in the cosmos. They allow us to directly witness the birth and death of black holes, to understand the extreme physics at play in neutron-star collisions, and to probe the very nature of gravity itself. It's like we've gained a new sense, a way to listen to the universe in a way we never could before, to hear the symphony of cosmic collisions. Imagine dropping a pebble into a perfectly still pond. The ripples that spread outward, carrying the energy of that initial disturbance across the water's surface, are analogous to gravitational waves. They carry the memory of the impact, the story of the event. If space-time itself can ripple, what does this suggest about its fundamental elasticity and dynamic nature? It's not just a passive backdrop, is it? It's alive, it's responsive, and it carries the echoes of the universe's most profound moments. It's a truly humbling thought, isn't it? But here's where it gets interesting, doesn't it? The universe itself, this vast, silent canvas isn't static. It's not some grand unchanging diorama. No, the universe itself is expanding, and this expansion subtly, beautifully, influences our perception of cosmic time. Think back to the early 20th century. A keen-eyed astronomer named Edwin Hubble, peering through his telescope, noticed something quite profound. He saw that galaxies, those distant islands of stars, weren't just hanging there. They were moving. And not just moving, but receding, drifting away from us. And here's the kicker: the farther away a galaxy was, the faster it seemed to be sailing into the cosmic distance. It was like looking out at a vast ocean and seeing every ship sailing away, with the ones on the horizon moving at a dizzying speed. Now, we might imagine this as galaxies simply moving through space, like ships on the sea. But that's not quite right. It's far more elegant, and perhaps a little more mind-bending. It's not that galaxies are moving through space, it's that space itself is stretching, like an invisible, elastic fabric. And as this fabric expands, it carries the galaxies along with it, like specks of dust caught in a gentle, growing breeze. Imagine you're on a giant, cosmic trampoline, and it's slowly, steadily being inflated. Everything on the trampoline moves apart. Not because they're walking, but because the very surface they're on is growing larger. And this stretching of space-time has a fascinating consequence for time itself. When we look at light from those incredibly distant, receding galaxies, that light has been traveling for billions of years. As space has been expanding all that time, the light waves themselves have been stretched. This stretching of light is what we call redshift. But it's more than just a color change. This redshift is also a subtle form of time dilation. Think of it like this: the signals, the messages of light from these ancient galaxies, are arriving to us, stretched out, arriving slower, arriving as if time itself has been gently diffused over the vast cosmic journey. It's as if the universe is whispering its ancient stories to us, and the further away the storyteller, the slower and more drawn out their words become. This expansion, this stretching of space-time, is what allows us to glimpse the universe's past. By looking at increasingly distant objects, we're essentially looking further back in time. A galaxy a billion light years away shows us the universe as it was a billion years ago. A galaxy 10 billion light years away shows us the universe as it was 10 billion years ago, perhaps when stars were just beginning to ignite their fiery hearts. It's like having a cosmic history book, where each page is a different epoch, and the further out we look, the earlier the chapter. It's a bit like blowing up a balloon, isn't it? Picture dots drawn on the surface of a balloon. As you inflate the balloon, the dots move farther apart from each other, not because they are walking or crawling across the surface, but because the surface of the balloon itself, the very fabric of the balloon, is expanding and stretching between them. Each dot represents a galaxy, and the balloon's surface is our expanding space-time. So, if the universe is expanding, and if time itself feels so wonderfully relative, so elastic, what does this imply about the very beginning of it all? What does it suggest about that initial spark, that moment when this grand cosmic unfolding began? It leads us to ponder even deeper mysteries, doesn't it? And here's where things get truly, wonderfully, mind-bending. Imagine we're gently rewinding the cosmic film, pulling back the curtain on the grand unfolding of everything. As we trace the universe's expansion, this incredible outward surge, all the way back, we arrive at a moment, a singular point, whereas time itself may have begun. It's like trying to find the edge of a dream, only to realize the dream is the edge. This brings us to the prevailing whisper of science, the story we tell ourselves about how it all started, the Big Bang Theory. It's not an explosion in the way we usually think of explosions, like a firecracker popping in the sky. Instead, it's more like the universe itself, everything we see and feel and are, emerging from a state of unimaginable density and heat, a tiny, potent seed from which space-time, matter, energy, all of it unfurled. Think of it as the universe taking its very first breath, a breath that has been expanding ever since. Now, here's a delicious paradox. If time began with the Big Bang, what was there before? It's a question that tickles the edges of our understanding, a philosophical knot that science grapples with. Can we even conceive of a before, when the very concept of before, of sequence, of duration, was born in that singular instant? It's like asking what color the silence was before the first note of music was played. The very fabric of time, that gentle rhythm we experience, might have woven itself into existence at that very beginning. But we're not left entirely in the realm of pure speculation. We have a tangible echo, a faint but persistent hum from that primordial moment. It's called the cosmic microwave background, or CMB for short. Imagine the universe right after its birth, still incredibly hot, a searingly bright dense plasma. As it expanded and cooled, this light, this ancient glow, eventually became free to travel. The CMB is that very light, redshifted by billions of years of expansion, bathing us in the afterglow of the Big Bang. It's a snapshot, a fossilized whisper, of the universe when it was only about 380,000 years old. It's like finding a single, warm ember from a bonfire that's now spread across the entire cosmos. The conditions in that early universe were, well, they were something else. Picture an incredibly dense, incredibly hot soup, so uniform that it's almost smooth. Almost perfect. In this primordial state, the fundamental forces that govern our reality, gravity, electromagnetism, the strong and weak nuclear forces, were likely unified, indistinguishable, like different facets of a single, brilliant gem. It was a state of pure potential, a cosmic womb where the blueprints for everything that would ever be were held in a delicate, fiery balance. The Big Bang, in this sense, is like the first, incandescent spark of a cosmic fire. From that single, impossibly energetic point, all the heat, all the light, all the structure that would eventually form stars, galaxies, and us, began to emanate. And the CMB. It's like the lingering warmth of that initial ignition, a gentle reminder of the immense power and the profound simplicity of that very first moment. And this leads us to a question that hums with curiosity. If the universe began in such a state of exquisite, almost perfect uniformity, how did the seeds of stars and galaxies, those intricate patterns we see scattered across the night sky, and their complex, beautiful dance with time, begin to form? What subtle whispers of asymmetry, what gentle nudges, set the stage for the cosmic ballet we witness today? What questions does this grand origin story spark in your mind about beginnings, about existence, about the very nature of reality itself? But here's where it gets interesting, truly interesting, because spanning the universe's history, this grand cosmic tapestry requires us to grasp an astonishing range of timescales. We're talking from the infinitesimally small, smaller than a whisper, to the unimaginably vast, stretching out beyond our wildest dreams. Let's start at the very, very beginning, almost before the beginning. There's this concept in physics, a mind-bending idea called Planck time. It's the smallest meaningful unit of time we can even conceive of, a fleeting flicker of existence at roughly 10 to the power of minus 43 seconds. Imagine trying to count that. It's so short that our current theories, our very understanding of how the universe works, kind of unravel. It's like trying to describe the color of a thought before the thought itself has even formed. Beyond Planck time, our physics books just go blank. Then, almost immediately after this almost non-existent moment, we have this inflationary epoch. This was a period of incredibly rapid, almost violent expansion of the universe. In a fraction of a second, smaller than you can even imagine, the universe ballooned from something smaller than an atom to something the size of a grapefruit, and then kept going, stretching out at an astonishing rate. It's like a cosmic breath, but instead of a gentle inhale, it was a universe-sized exhale that happened in the blink of an eye, or rather, in less than the blink of an eye. After this explosive beginning, things started to calm down, but only relatively. It took hundreds of millions of years, a vast expanse of time that dwarfs our entire human history, for gravity to do its patient work. Gravity, that invisible hand, began to pull together the primordial gas, the leftover stardust from that initial fiery burst. Slowly, painstakingly, it gathered these wisps of hydrogen and helium, coaxing them into denser and denser clouds, and eventually, after all that waiting, the very first stars began to ignite, like tiny sparks in an immense darkness, marking the dawn of stellar light. From there, the story unfolds over billions of years, billions. We're talking about the slow, majestic ballad of galactic evolution. Galaxies, those swirling islands of stars, began to form, merging and interacting, shaping each other over eons. Within these galaxies, star clusters coalesced, and around countless stars, planetary systems, like our own humble solar system, began to assemble. It's a story of cosmic accretion, of dust and gas clumping together, of gravity's relentless sculpting, all playing out on a stage measured in the lifespan of civilizations, and then some. Imagine a cosmic timeline stretching from that single, impossibly small point of Planck time to an endless, shimmering horizon. We traverse this line, don't we? We witness events happening in breaths, in heartbeats, in lifetimes that are so long they're almost geological, and then in epochs that dwarf our entire human existence, making our history feel like a single, fleeting exhale. And as we synthesize these vast timescales, these mind-bending relativistic effects, these incredible stretches of cosmic time, how does it all inform our understanding of our own fleeting moment in this grand cosmos? It's a question that hums, isn't it? A gentle inquiry into our place within this immense, unfolding story. Take your time with this thought, won't you? Our perception of cosmic events, and their timing, is profoundly shaped by our own position and motion within this vast, shimmering tapestry of space-time. It's like we're all standing on different shores, watching the same ocean, but our experience of the waves, the tides, the very rhythm of it all, is uniquely ours. You see, in the grand theater of physics, there's this beautiful principle. The physical laws themselves, the fundamental rules of the universe, they remain the same for everyone, no matter how you're moving, as long as you're moving at a constant speed in a straight line. We call these inertial frames of reference. Think of it like this: whether you're sitting still on a park bench or gliding smoothly in a perfectly silent train, the way a ball falls when you drop it, the way light bounces off a mirror, those fundamental interactions are identical. But here's where it gets wonderfully strange. While the laws are the same, the measurements we make, the length of that ball's fall, the duration of its journey, those can be quite different depending on your vantage point, on your own particular motion. And at the heart of this relativity, this beautiful dance of perspectives, is the speed of light. This isn't just a speed, it's the universe's ultimate speed limit, a cosmic speed bump that nothing with mass can ever truly reach. It's the speed at which information itself can travel, the messenger that carries the whispers of distant stars across the void. And because of this unwavering, cosmic constant, our very sense of simultaneity, the idea that two events happen at the exact same moment, well, that's not as absolute as we might think. What is simultaneous for one observer might not be for another, all because of how light has to travel to reach their eyes. Think about the Doppler effect, that familiar shift in pitch we hear when an ambulance siren races towards us, then speeds away. As it approaches, the sound waves get compressed, higher pitched. As it recedes, they stretch out, lower pitched. Light does something remarkably similar. When a celestial object is moving away from us, the light waves it emits get stretched, shifting towards the red end of the spectrum. We call this redshift. Conversely, if it's moving towards us, the light waves bunch up, shifting towards blue shift. This isn't just a pretty color change, it's a direct indicator of relative motion, subtly altering the perceived timing of events and the very frequencies of light that reach us. And then there's gravity, the gentle sculptor of the cosmos. Massive objects like stars and galaxies don't just sit there, they warp the very fabric of spacetime around them. This warping can bend the path of light, like a cosmic magnifying glass. When light from a distant galaxy has to travel around a massive object in between us, it can take multiple paths. Some paths might be shorter, some longer. This means we can see multiple images of the same object, and crucially, the light from those different paths can arrive at our telescopes at different times. So, even the journey of light, the very messenger of cosmic events, is subject to delays and detours dictated by the gravitational landscape. It's a bit like watching a distant train. You hear the whistle, and as it approaches, the sound seems to get higher, sharper. Then, as it passes and moves away, the pitch drops, becoming a mournful hum. That change in pitch tells you something fundamental about the train's motion, its relationship to you. In a similar way, the light from celestial objects carries these subtle clues, these shifted frequencies, telling us about their own motion and the spacetime they traverse. It's like the universe is whispering its secrets, and the Doppler effect is one of its languages, subtly affecting how we perceive the timing of those cosmic whispers. So, if our observations, the very data we gather about the universe, are so deeply intertwined with our own unique frame of reference, with our motion and our place within the gravitational currents, what can we truly say about the objective nature of cosmic time? Is there a single, universal clock ticking away the moments for all of existence, or is time itself a more fluid, personal experience, painted by the brushstrokes of our own journey through the cosmos? It's a question that invites us to ponder, to lean into the mystery, and to appreciate the profound beauty of our relative place in this grand unfolding story. But here's where it gets interesting, doesn't it? Beyond the physics, beyond the grand cosmic dance of galaxies and the slow burn of stars, time is also a fundamental dimension of our conscious experience. It's what shapes our reality, what gives it texture and form, like the subtle grain on a piece of aged wood. Let's start with what we feel as a now. Philosophers have a lovely term for this, the specious present. It's not just an instant, a razor-thin edge between past and future. It's more like a tiny shimmering duration that we consciously perceive as the present moment. Think of it as a small bubble of awareness, holding together a sliver of what just was and a hint of what's about to be. It's the fleeting breath we take, the single note of a melody that lingers just long enough to blend into the next. Without this tiny pocket of now, our experience would be a dizzying, disconnected jumble of sensations. And of course, our consciousness doesn't just exist in this fleeting present. It's a masterful weaver, constantly pulling threads from the past and the future to create the rich tapestry of our lived experience. Our memories aren't just static files stored away, they're living echoes, coloring our perceptions, shaping our reactions. And our anticipation, our hopes and fears about what's to come, they're equally potent forces, pulling us forward, guiding our steps. It's like standing on a riverbank, watching the water flow. You see the ripples of what's just passed, and you can sense the currents that are approaching, all within your present view. This weaving of past, present, and future is how we construct narratives. We are storytellers, aren't we? We build a personal timeline, a winding road of experiences that gives our existence meaning and structure. It's the story of our lives, with its beginnings, middles, and perhaps eventual ends. This narrative thread is what helps us make sense of the chaos, to find patterns in the seemingly random occurrences. It's like looking at a constellation in the night sky. Individually, the stars are just points of light, but by connecting them, we create a story, a bear, a hunter, a queen. And this leads us to a rather delightful philosophical puzzle, this perceived flow of time. Does time actually flow like a river, carrying us along its current? Or is this feeling of movement, this sense of progression, something our minds create? Is it a construct, a way for our consciousness to make sense of change, to process the constant unfolding of events? Perhaps the universe itself exists as a vast, unchanging block, and our consciousness is simply moving through it, like a spotlight illuminating different scenes. It's a thought that can make your head spin in the most wonderful way. You see, our conscious experience of time is a bit like reading a book. We turn the pages, moving through chapters, linking events, building a story in our minds. But the entire story, every word, every plot twist, exists simultaneously on those pages, waiting to be discovered in sequence by our reading. We are the readers, experiencing the unfolding narrative, but the book itself, in its entirety, is already there. As we begin to integrate the vastness of cosmic time, those aeons of stellar evolution and the slow, patient work of the universe, with our own deeply personal experience of moments and memories, what profound reflections emerge? What do we discover about our own fleeting, yet infinitely precious, place within this grand temporal tapestry? It's a question that invites us to lean in, to listen to the whispers of time, both within us and all around us. Now, here's the truly breathtaking part, isn't it? The very stuff that makes up you, that makes up me, that makes up this very planet we're standing on, was once dancing in the fiery hearts of stars that lived and then, in spectacular fashion, died billions and billions of years ago. It's a story that begins in the deep, dark wombs of the cosmos. Stars, you see, aren't just distant pinpricks of light. They are cosmic furnaces, churning out the very building blocks of everything we know. Inside their incandescent cores under unimaginable pressure and heat, a process called stellar nucleosynthesis is constantly at work. It's like a grand alchemical transformation. Hydrogen, the simplest element, is fused into helium. Then, as stars grow older and hotter, they forge heavier elements. Carbon, the backbone of life, is born. Oxygen, the breath we inhale, is created. And even iron, the stuff of our blood, that metallic tang on your tongue, it all originates in the fiery crucible of a star. But the story doesn't end with the star's quiet hum. Many stars, especially the larger ones, meet a more dramatic end. They explode in a cataclysmic event called a supernova. Imagine the most brilliant fireworks display you can conceive, magnified 1,000,000,000,000 times. In these explosive finales, even heavier elements are born: gold, silver, uranium, all the precious and rare materials that make our world so rich and varied. And what happens to all these elements, these newly forged cosmic ingredients, after the star has finished its grand performance? They are flung out, scattered like seeds across the vast interstellar medium. They drift through the darkness, mingling with gas and dust, waiting for their next act. And it's within these swirling clouds of stardust, these remnants of stellar lives and deaths, that new stars and new planets begin to form. Our own sun, that warm, familiar presence in our sky, coalesced from such a cloud, a celestial recycling project billions of years in the making. And Earth, this beautiful blue marble, gathered its materials from that same ancient stardust. So, when we say we are stardust, it's not just a poetic phrase. It's a literal truth. Every atom in your body, from the calcium in your bones to the iron in your blood, from the carbon in your cells to the oxygen you're breathing right now, has a story that stretches back to the birth and death of stars. We are, in the most profound sense, cosmic descendants. Our physical existence is woven from the fabric of stellar evolution, a tapestry spun from the ashes of ancient suns. Think of the universe as a grand cosmic bakery. Stars are the ovens, impossibly hot and powerful, where the fundamental ingredients of existence, the elements, are baked. And when these stellar ovens expire, they don't just vanish. Oh no. They scatter these newly baked goods, these precious elements, out into the vast cosmic kitchen. And then, over eons, these scattered ingredients drift, they gather, they swirl, and they combine in intricate, beautiful ways, eventually forming complex and wondrous creations, like us. We're the intricate pastries, the delicate cakes, baked from the finest stardust. As we stand here, composed of these ancient, celestial fragments, how should we contemplate the vastness of time and the universe that birthed us? It's a humbling thought, isn't it? To realize that the very elements that allow us to think, to feel, to experience this moment, have witnessed the rise and fall of cosmic empires, the birth and death of galaxies. We carry within us the echoes of supernovae, the whispers of dying stars, the silent, patient dance of cosmic creation. It's a lineage that connects us not just to our immediate ancestors, but to the very dawn of time itself. And in that connection, there's a profound sense of belonging, a deep, quiet understanding that we are part of something so much larger, so much older, and so incredibly beautiful. But here's where it gets interesting, doesn't it? Understanding how these celestial giants, these of luminous hearts of the cosmos, shape spacetime, also gives us these tantalizing clues about the universe's ultimate fate, and perhaps the future of time itself. It's like looking at the embers of a magnificent bonfire and trying to imagine the quiet night that follows. We've seen how gravity, this invisible sculptor, bends the very fabric of reality, creating the gentle curves that guide the dance of planets and stars. But the universe isn't just about graceful orbits. It's also about a grand, cosmic expansion, a stretching of the canvas on which everything is painted. And lately, scientists have discovered something quite peculiar about this stretching. It's not just happening, it's accelerating. Like a breath held too long, the universe is pushing outwards with an unseen force, a mysterious tug we've come to call dark energy. It's this invisible hand that's gradually, but persistently pushing galaxies further and further apart. Think about our own Milky Way, a swirling island of starlight. In this accelerating future, even our nearest galactic neighbors will eventually recede beyond our sight, becoming distant, faint whispers in the cosmic dark. And the stars themselves, these brilliant furnaces that have illuminated our skies for billions of years, they too have their own life cycles. They are born in nebulae. They blaze with glorious light, and then, eventually, they begin to fade. One by one, they'll exhaust their fuel, becoming white dwarfs, then perhaps neutron stars or even black holes, their brilliant fires slowly cooling, their energetic dance coming to a gentle halt. The universe, in this grand unfolding, is predicted to become a vast, cold, and dark place. This leads us to a rather profound, and some might say, melancholic, thermodynamic concept, the heat death of the universe. Imagine a perfectly insulated room, filled with warmth. Over an immeasurable stretch of time, that warmth, that usable energy, will naturally spread out, becoming more diffuse, less concentrated, until eventually everything in the room reaches the same uniform temperature. There are no more hot spots to drive processes, no more gradients to create movement. This is the universe approaching a state of maximum entropy, a profound equilibrium where all the energy that once fueled the vibrant dance of creation has been so thoroughly spread out that it's no longer zeros usable. It's like a magnificent symphony that has played its final, lingering note, and now only silence remains. And what of time in such a distant, cold, and dark universe? If the stars have all winked out, if galaxies have drifted beyond each other's reach, if all activity has ceased, what does time even mean? Perhaps it becomes almost imperceptible, a slow, gentle tide that barely stirs the quiet waters. Without events to mark its passage, without the ticking of cosmic clocks, time might become a vast, unbroken stillness, a timeless ocean of quietude. It's a thought that can feel both a little daunting and, in its own way, incredibly peaceful. Imagine a grand, intricate clockwork that has been running for eons, its gears turning with precision, its springs wound tight with cosmic energy. As its energy source dwindles, its movements become slower and fainter, until eventually, it winds down into a state of quiet stillness. The hands might still be there, pointing to a forgotten moment, but the mechanism that drives them is no longer active. That's a little like our universe in its twilight. Having explored the intricate relationship between time and stars, between gravity and the very unfolding of existence, what final, gentle thoughts can we carry with us as we conclude our journey through these celestial chapters? It's a question that lingers, like the scent of stardust on a quiet night. Take your time with this thought, friends. The universe isn't just a collection of stuff, scattered like pebbles on a beach. It's a symphony. A grand, unfolding, interconnected symphony played out across the very fabric of space-time. Think about it. Gravity, that gentle, insistent tug that keeps our feet on the ground and the moon in its orbit, it's not some separate force acting on things. It is the curvature of space-time itself, a ripple in the cosmic pond. And that curvature, it's directly influenced by mass and energy. So, the life cycle of a star from its fiery birth in a nebula, through its long luminous life, to its eventual dramatic collapse, perhaps into a neutron star, a dense ember, or even a black hole, a silent maw in the cosmos, all of that shapes space-time. And what about the heart of a star? The nuclear furnace where elements are forged. That dance of protons and neutrons, the release of immense energy, it's all governed by the fundamental forces, by quantum mechanics, by the very rules that dictate how matter interacts. These aren't isolated events, you see. The nuclear processes within a star create the very mass that curves space-time, and that curvature, in turn, dictates how light and matter will travel, how galaxies will dance together. It's an exquisite, cosmic feedback loop. Relativity tells us that as objects move faster or as gravity gets stronger, time itself stretches and warps. So, a star's immense gravity, its energetic core, its very motion through space, it's all woven into this tapestry of space-time. Space-time itself, it's not just an empty stage where cosmic plays unfold. Oh no. It's an as-active participant. It's the canvas darn the paint. It's the resonant hall that carries the music of existence. Imagine it like a vast, cosmic orchestra. The stars are the instruments, each with its own unique tone and melody, its own life cycle of creation and transformation. Gravity, that invisible maestro, conducts the grand performance, shaping the movements, the harmonies, the very rhythm of the cosmos. And space-time. Space-time is the resonant hall itself. It's the very air that carries the sound, the walls that echo with the music, the space that allows the symphony to unfold and to be heard, across unimaginable distances and through the vastness of time. It's not just a backdrop, it's the medium through which the music of creation travels, vibrating with the energy of every exploding supernova, every colliding galaxy. And the beauty of it all, isn't it just breathtaking? These physical laws, these fundamental rules that govern everything from the smallest subatomic particle to the largest galactic cluster, they possess an almost poetic elegance. They're like a universal language, a set of intricate instructions that, when followed, create such astonishing complexity and order. It's like finding a perfectly crafted sonnet written in the language of physics. Despite the immense, sometimes violent, processes at play, there's an underlying harmony, a deep-seated order that we can, with effort, begin to perceive. It's a testament to the universe's inherent structure, a structure that allows for such incredible diversity and dynamism. And where do we fit into this magnificent, unfolding performance? We, with our fleeting breaths and our curious minds, are the conscious observers. We are the audience, yes, but more than that, we are the ones who can listen. We can appreciate the grandeur, the subtle nuances, the sheer, overwhelming beauty of this cosmic symphony. We are the ones who can feel the vibrations of starlight on our skin, who can gaze up at the night sky and feel a deep, resonant connection to those distant fires. We are part of the symphony, in a way, our consciousness a unique instrument capable of perceiving and reflecting the universe's own song. As we prepare to gently transition from this exploration, to let this feeling of cosmic interconnectedness settle within us, what lasting sense of wonder can we hold on to? Perhaps it's the understanding that we are not separate from this grand performance, but an integral part of its unfolding melody, capable of experiencing its profound beauty. But here's where it gets interesting, doesn't it? The very act of contemplating these cosmic timescales, these vast stretches of existence that dwarf our own brief flicker, can offer us a profound sense of peace and perspective. It's like standing on a shore and watching the immense, timeless ocean, isn't it? We can feel a sense of awe, a touch of insignificance perhaps, yet also a deep, resonant connection to something eternal and beautiful. When we think about the life of a star, not just the gentle glow we see, but its entire journey from a swirling nebula, a cosmic cradle of gas and dust, to its fiery birth, its long, steady burning, and then its eventual, sometimes dramatic, farewell, we're talking about timescales that are almost impossible for our human minds to truly grasp. Our lives, even the longest and most celebrated, are like a single breath in the grand exhalation of the universe. A star can burn for billions of years, its light traveling across unimaginable distances, carrying stories of creation and transformation, our own human history, all our triumphs and heartbreaks, our art and our wars is a whisper in that stellar symphony. And in that contrast, in that stark difference between our fleeting existence and the enduring presence of the cosmos, there's a curious kind of liberation. It can feel overwhelming, I know, to realize how small we are, how brief our time here truly is, like a tiny speck of pollen carried on a hurricane. But it can also be incredibly freeing. If our individual lives are so temporary, so ephemeral, then perhaps the pressure to achieve everything, or to be remembered forever, loosens its grip. It allows us to appreciate the simple, profound gift of being here, right now. It's like realizing you don't need to build a monument, you just need to feel the sun on your skin, the earth beneath your feet, the air in your lungs. This vastness, this sheer immensity of space and time doesn't diminish us. In a strange way, it can magnify the preciousness of our present experience. We are, after all, made of stardust, woven from the very elements forged in the hearts of ancient stars. That connection, that fundamental kinship with the universe, is undeniable. Even as we unravel some of its secrets, as our scientific understanding expands like the universe itself, there are always deeper mysteries waiting, aren't there? Like peering into a well that seems to have no bottom, or gazing at a night sky that stretches into infinity. This enduring sense of wonder, this gentle curiosity about what lies beyond our current understanding, is a vital part of our human journey. It keeps our spirits alive, our minds open, and our hearts ready to be surprised. And so, in the grand tapestry of cosmic time, where stars are born and die in slow, deliberate dances, our own lives unfold in a vibrant, fleeting present. It's in this present moment, this sliver of now, that our consciousness, our awareness, our various experience of the universe takes place. It's the only place we truly exist, the only stage upon which our personal starlight can shine. Whether it's for a blink of an eye or for eons, the quality of that light, the depth of that experience, is what truly matters. It's where the whispers of eternity find their echo in our own beating hearts. And so, we find ourselves at the quiet edge of our cosmic wanderings. We've journeyed through the bending fabric of spacetime, witnessed the birth, life, and dramatic deaths of stars, and seen how these cosmic titans warp the very rhythm of time. From the gentle embrace of relativity to the cataclysmic events of supernovae and the enigmatic depths of black holes, we've explored how time is not a constant, but a fluid, dynamic dimension intricately woven into the universe's grand design. We've seen how pulsars tick with cosmic precision, how the universe expands, and how even our own existence is a testament to the recycling of stellar matter across unimaginable epochs. As we conclude this exploration, let us carry with us a sense of profound connection. We are made of stardust, our lives brief but luminous moments within an ancient, evolving cosmos. The vastness of cosmic time, while humbling, can also be a source of deep peace, reminding us that our concerns, while vital to us, are but fleeting ripples in an immeasurable ocean. The universe's slow, deliberate dance of creation and destruction, governed by elegant laws, offers a mirror to our own existence. Let us embrace the mystery, cherish the present, and find wonder in the quiet, persistent whisper of eternity that surrounds us, a gentle echo in the grand, silent symphony. Thank you for joining me on this journey through slow time and the secret life of stars. Your presence and curiosity enrich this space, like tiny stars igniting in the vastness. Please share your thoughts, your lingering questions, or any insights gained in the comments below. Your reflections often illuminate new perspectives for us all, like constellations appearing where none were seen before. Consider sharing this video with anyone you feel might find solace or wonder in its gentle exploration of the cosmos. Now, as this journey gently concludes, allow yourself to drift. Let the vastness of space and the slow, steady heartbeat of the cosmos lull you into a deep, restorative rest. Feel the gentle pull of gravity grounding you, the soft glow of distant stars comforting you, like a warm blanket woven from moonlight. Breathe in the quiet of the universe, and exhale any lingering tension, letting it dissolve into the cosmic dust. May your dreams be as peaceful and expansive as the night sky itself. Sleep well, and until we meet again on conscious frequency, may your moments be filled with gentle peace.